Yeah, sure. Hello, everyone. Thank you very much for joining. Today, I'm going to talk about multiple randomization design. And this is this paper has not been published yet. It is in archive as of December 2021. And this is a research between researchers at Stanford and University of Washington and Amazon. And one of the authors of the paper, Huido Imbens, he won the Nobel Prize in 2021 in economics, along with Josh Angris and David Card for their contributions to causal inference research in economics. And this is Huido Imbens. He's an economics professor at Stanford University. And as I said, along with Josh Angris, I think he's at Harvard or at MIT, and David Card, they won Nobel Prize last year. And what is the subject of this paper? What they do is they introduce a very novel technique for randomization design to infer causality. And this is in context of Amazon, and I'm going to explain a bit more of what they exactly do here. This is in context of Amazon because they were interested in researching the policies they come up with, like changing prices or faster shipping or adding reviews to products or showing more pictures and videos of products, or basically having different policies, how much impact that has on a particular outcome, which can be purchase of that product or basically demand for a product or things like that. They wanted to measure that accurately, so they teamed up with the Amazon team teamed up with professors at Stanford and Washington University to basically come up with this research. And this is a very novel research. In previous social science randomized controlled trial research would be a special case of this research. This is much more general and much more encompassing. So in order to start, one of the most useful methods in social sciences and economics to measure causal inference is by A/B testing, or another name for that is randomized controlled trial, or RCT, where we divide people into two groups. We have one control group and one treatment group, and we do this split between the control and treatment group in basically random. So each person has equal likelihood of being in the control group or in the treatment group, and then to the treatment group, a treatment or an intervention or a policy is basically given, and to the control group it is not given, and then at the end they measure outcome. In order to basically explain this in a better way, let's think about COVID vaccine, right? So for example, let's assume Pfizer wants to see if the vaccine they have developed is efficient in basically containing COVID virus. So what they do is that they have, let's say, 10,000 people from all over the world, from different ages and different backgrounds and race and everything. And then they divide these 10,000 people equally into two groups of 5,000. And they basically, one group would be treatment, they would get the basically vaccine, and another group would not get the vaccine. And then after a while they measure an outcome, they compare them, and if they see a difference between the treatment group and the control group, because the assignment was randomized, they will say that this change is causal, and then they go ahead and get approval for the vaccination. So this was in the context of clinical studies, and that's why they're called clinical trials. But in the social sciences, this basically takes place as well. One of the oldest examples is for Neyman and Fisher. They performed these experiments on agricultural products on basically different pieces of land. They would try different fertilizers, and they would sort of attribute the outcome to the impact of the fertilizer. So they would come up with causal experiments in that way. So as I mentioned, there is we have a treatment group, treatment A, and we have treatment B. Another name for treatment B is control treatment, or meaning no treatment at all. And this has been the subject of studies in social sciences for a long time. What they do in this paper is that they change the design of this randomization. Instead of saying by a flip of a coin, each participant can be assigned to a treatment group or control group, they do some advanced randomization, which I'm going to talk about in a second. So they start their paper by an introduction about causal effects of a binary treatment. As I mentioned, basically member of the population, they can be individuals, it can be products, even products can be randomized. In the case of Amazon, they what can be randomized can be, for example, if they add reviews to the products, what would the effect of that be? Or if they basically show the name of the seller, what is the effect of that? Or if they show videos of a product, is that very helpful or not? It can be firms, it can be plots of land, it can be even time periods. It can be if we, for example, have this sale on Black Friday, does that have causal impact on basically more sales than another day? So it basically anything can be randomized, and they basically cite some very important papers from Fisher and Neyman and Holland, Wu, Hamada, Imbens, and Rubin. And Imbens is actually one of the authors of this paper as well. And they basically start their paper by talking about what has been done before, and then what they come up with is an addition to what has been talked about. So before I dive into what they talk about, they talk a lot about the Rubin model in this paper. And what Rubin causal model is exactly the same thing that I just talked about. Each person has equal basically chance to be in the treatment group or control group, and the way this causal impact is being measured is that they have potential outcomes. That's what they call it. Potential outcome of basically, let's say potential outcome is being treated with COVID vaccine if you're in treatment group, and potential outcome of basically treatment if you're in control group. And this can be done within a group of people, in which case the potential outcome of people in the treatment group gets averaged, would be divided by the number of people in control and in treatment, minus potential outcome of people in control group divided by their number. So this is what Rubin causal model is, which gives us average causal effect. Now, what they argue in this paper is that these people that are in treatment group, they interact with one another, and they may interact with people in the control group. In the case of Amazon, for example, let's say Amazon has a new policy that they want to see impact of basically faster shipping, let's say 1-day shipping on sales of products, right? So if they do that, if they want to divide people into two groups, one would be treatment and one would be control, people in treatment group will take advantage of that policy, and they may talk to control group people as well, because information gets shared, and some control group may also use that policy. Or this sort of policy, faster shipping, that treatment people are exposed to, may change their opinion, may change their idea about what product they want to buy. For example, if they know that they want to buy product X and they will get it in 10 days, there would be a difference between that and if they had an option to get a product in maybe one day. Maybe in that case, they would change their mind and don't want that product anymore. They want to switch to another one. So these are in economics, these are called spillovers and basically interferences that these classical Rubin causal model cannot handle, and that's why we need multiple experimental designs. And I'm going to explain more what they are in a second. So what they do is they talk about buyer experiments and seller experiments, and what they are is that I think it would be more clear if I explain on the matrices they talk about. So in the case of buyer experiment and seller experiment, so what we see here, each row in the matrix W, each row is a customer. So let's say this is person I, this is person one, person two, person three, and person four. So each row is a person or is a buyer basically, right? And each column, let's say each column is a different product, or they call it seller. I mean, it can also be a product. For example, let's say column one is a coffee maker machine, basically company. Column two is a tea making basically machine company. In column three is juice making machine company, right? So columns are different products or sellers or companies, and each row is different people or different individuals. And in the traditional basically experiment design, seller experiment would be, okay, so what we do is we will randomize one particular product or one particular item, and that would be the only thing different people will see across the board. In this case, we have 2 products out of 1, 2, 3, 4, 5, 6, 7, and out of 8 products, 2 of them, let's say the treatment, okay, so C is the control and T is treatment. Let's say treatment is having faster shipping, right? Let's say Amazon decides to have faster shipping on tea making machines, and let's say I don't know, vacuum cleaners, right? Let's say on only these 2 products, Amazon decides to have faster shipping, and then people are exposed to these products the same. So this is a conventional case where at the end of the experiment, we will see that for product number 2 and product number 8, where we had faster shipping, how much more sales we had compared to the control groups, where are products that basically we did not have faster shipping, right? So this is called seller experiment, meaning that product or what seller is providing is being randomized and is being in the treatment group or control group. Another case is buyer experiment, which is also traditional and basically classic and what has been around so far. Let's say we still have 4 basically customers, right? And here we're not randomizing products, we're randomizing people. And let's say person number 2 is being randomized, and let's say the treatment is something like maybe the same as above. Maybe the treatment is faster shipping. We want to see if person 2 gets faster shipping on all these 8 products, what would be the outcome compared to other people who would not get faster shipping on either of their products. So this is the case of having one person having completely in the control group, or having one product completely in the control group. So this has been the case so far. But what they come up with in this paper, and this is the interesting part, is that they have multiple design, and what it means, let me zoom in a little bit. So we still have the same situation. We have our buyers in the basically row of the matrix, and we have our products in the columns of the matrix. But what they do is that the treatment is not homogeneous across the board. For example, in the previous case, in the buyers experiment, we saw that treatment was assigned to one person across all products, But here in this case, for example, for person 3, we see that this person 3 is in the control group for the first 4 products, and control group meaning not having faster shipping on items 1, 2, 3, and 4, but is experiencing faster shipping on products 5, 6, 7, and 8. So this is person 3 is not completely either in the control group or is not completely in the treatment group. So, and the reason they basically do this design is that they want to capture a spillover effects, and I'm going to talk about that a bit more. So persons 3, 4, and 5 are experiencing no fast shipping on items 1, 2, 3, and 4. That's why they are basically separated with color green here. They are still in control group. That's why we have C here, because they're not seeing faster shipping. But the difference between the green C's and the red C's is that people over here, 3, 4, and 5, at some point they do get fast shipping for items 5, 6, and 7, but people 1 and 2, they do not get fast shipping at any point in their basically experience shopping on Amazon. So for example, and the reason this is important is that, let's say person 4, okay, so for example, let's say person 1 has wants to shop on Amazon. They don't have any fast shipping option available to them, so they may make the decision one way, right? But person 5 has fast shipping on items 5, 6, 7, and 8, and no fast shipping on items 1, 2, 3, and 4. So this may impact their decision. They might want to prefer to order something that basically arrives faster. So the person 5 in basically when they want to decide to whether buy this item 3, is different from person 1 trying to decide to buy item 3, because person 5 has a faster shipping option as well. So this might impact their behavior. So this was at the buyer's level, but at the seller's level, we can also have that randomization too, which is, for example, product 8 is basically having faster shipping for person 3, 4, and 5, but is not does not have fast shipping for persons 1, and 2. So this may also have impact. So that's why we have these blue C's over here, and there's a difference between people here that have blue C and red C, because I'm sorry, I should not have said people, products, because products that have blue C are different from red C. For example, product number 2, right? This product number 2 is basically being shown to all people 1, 2, 3, 4, and 5 without having option for faster shipping. But this product 7 is being shown to person 1 and 2 without faster shipping, but to persons 3, 4, and 5 with faster shipping. So there may be a difference in purchases of item 2 and 7. So we have to look at them basically differently, right? So there are 3 types of controls basically over here in this experiment design, whereas previously in the Rubin causal model or the randomized control experiments that so far everyone has been using, we had 1 control and 1 treatment. But in this design, we have 1 treatment and 3 controls. And if we want to see the impact of basically spillovers, for example, if you want to see if we gave person 4 faster shipping option, how that impacts the decision, instead of in this case, Rubin causal model subtracting basically potential outcomes of treatment from the control group, right? Instead of doing this treatment and control, we would get the outcome from the treatment group and then subtract it from only the green C's, because in this case we are interested in the spillovers across different products. Or if we are interested in spillovers across different buyers, for example, buyers might talk to one another about the policy that has been changed, then we can measure the impact in the measure the outcome in the treatment group and then subtract that from the outcome in blue control group, because in this case we can see the difference between this randomization. And then in the paper they talk about how we can combine all these three control groups, their outcome, to come up with an unbiased estimator for causal inference. So their rationale for having this is twofold. The first one is that they wanted to measure the causal impact more accurately because of this because of the spillover effect, and also they wanted to measure a spillover effects and basically interactions that occur between treatment and controls. So before I explain more what they do in this paper, does the experiment setup make sense? Does anybody have any questions about the setup here?
Morteza, thanks. Sorry, I missed what was the definition of CMT in this case?
Sure. C is people who are in the control group, meaning they do not get the treatment. T is people who are in treatment group, meaning they do get the treatment. And treatment here is faster shipping option from Amazon.
And the color code doesn't mean anything, right?
The color code, what it means is that green are basically people that they so the columns are sellers or products, and the rows are people or buyers. So color green are that basically people that are in the control group, meaning they don't get the faster shipping options for products 1, 2, 3, and 4, but at some point they do get faster shipping options for product 5, 6, 7, and 8, meaning they are in the control group in the sense that they don't get faster shipping for these products, but they do get faster shipping on some other products, and this may impact their decision purchasing behavior. So this is the green one. The red ones are people that they don't ever get faster shipping options on either of their products. So these are a little bit different from the green ones, which they at some point do, and the blue ones are basically buyer product pairs that basically is in the treatment group for some people and is not in the treatment group for some other people. So there are tiny differences between different Cs. Are there any other questions regarding the experiment design? So what then they talk about is this matrix W, which is this, and each person has the option to be in treatment group and control group, and they basically talk about some examples that this experiment design can be applied to, right? Policies can impact people's behaviors in so many ways. For example, they talk about ride sharing, where drivers choose to accept ride requests from riders at different times. For example, Uber and Lyft, or for example, travel websites with air travelers search for flights offered by airlines or travel agencies, right? So these are different. Basically, instead of having buyers and sellers, we can have online agency and basically airline agency and travel agency, or we can have a different time points, or we can have social media platforms. We can have Instagram, YouTube. There are interactions between people. That's why we can have these multiple randomized experiments. So MRD, we're gonna see that in the paper, is short for multiple randomized experiments. They talk about this a little bit more, and they formalize what they want to do. So what they show here in this part of the paper is the basically simple multiple randomized design. This is the most simple this can be in basically designing the multiple experiment, but it doesn't have to have this shape or format. For example, this is another example that they show, is that they said, okay, so we can have for here the experiment setup is the same. Here in this matrix, each row corresponds to buyers, and let's say person 5 has basically this experience shopping on Amazon. It is in control group in some case for some products. It is in treatment group for some other products. And as you see, this is different from what we saw above. Here, products are divided into 2 groups. Products also is within the products we have buyers experiment and we have sellers experiment. For example, we have 8 products, right? And these products can be coffee machine, tea maker, or anything that we have on Amazon. And for one set of products, we can have all basically for person 1, we can have all these products be in the control group, meaning not have fast shipping on these products. So we can have this experience for person 1 and 2, but for person 3, we can have all these 3 products in the treatments, meaning having faster shipping for these products. On the other hand, for sellers, we can have another experiment, meaning for products 4, 5, 6, and 7, we can do randomization vertically instead of horizontally. We can have product 4 being all in the treatment group, meaning having faster shipping for product 4 for everybody, and product 5 we cannot have fast shipping for anybody for product 5. And here as we see, the treatment is the same, is faster shipping on these items, but control groups are being different because, for example, green C is for person 1, basically is the seller buyer pair or the product buyer pair for the items that at some point they are exposed to treatment for a product, meaning let's say person 1 is, for example, myself, Morteza does not get fast shipping on items 1, 2, and 3, but gets fast shipping on item 4 and item 6, right? And so this is basically me trying to buy a coffee maker over here, and this is a teapot, and this is something else. At the same time, this coffee maker that I'm trying to buy is also being randomized vertically, meaning it does not have faster shipping option for me being Morteza, but for another person, number 3, this coffee maker is being randomized to have treatment. So this C is different from, for example, this C that Morteza wants to buy, let's say, a vacuum cleaner, that this vacuum cleaner does not become basically randomized to anybody across the experiment. It does not have faster shipping at all, but it has faster, but me trying to buy this vacuum cleaner, I also have the option to have a faster shipping item 6, for example. And their rationale in the paper is that having this C is different from having this C, because this C, for example, is basically has faster shipping item for person 3, and let's say person 3 really likes the faster shipping, they go ahead and buys item 1, and basically person 5 really likes faster shipping too, and they go ahead and buy item 1 as well. And as a result, the price of item 1 might change. And if the price of item 1 changes, then the control group that Morteza is in is very different from this control group, where item 8 does not become randomized at all. So, and this is what they call a spillover effect. I hope I was able to explain this properly. It's a little bit complicated, but extremely useful as well. So they talk about the experimental design after this, and then they basically go back to the literature, because obviously this Rubin causal model has a lot of limitations and is very limited in a scope. They in the paper talk about what other people have done to overcome this challenge, this limitation of basically a spillover effect within treatment and control groups. So what they do is they cite some papers. One of them here they talk about is that people, Cochrane and Cox and Brown and Boginoff, what they have done in their work has been they looked at both treatment group and control group at different times. And they, for example, in the case of Amazon, let's say we would not have 3 different control groups. We would have 1 control group and 1 treatment group, but we look at them through different time points. And we another name for this is phase-in design, meaning the treatment is being given to treatment group over time, and they can compare the different behaviors among them. This is very useful, but is not very accurate, because over time a lot of things changes and a lot of other variables come into effect as well. So that's why they sort of rule out this possibility. Another thing that has been done is a split plot design, work by Yates, Brandt, and Jones, where, for example, they say, for example, they have, let's assume they have multiple primary units, or for example, plots of land in the case of agricultural studies, and they have different lands, and they divide each land into subgroups, and then they do randomization within the subgroup, and they try to basically control for different spillover effects within each land or within each subgroup. And in the paper, the authors of this paper, they say that this also rules out because there are correlations between subplots within a land. So we cannot, for example, for an let's say a plant or in an agricultural study, if you want to look at subplots which are, for example, randomized within a land, there are correlations because they are still part of the same land. One study that really has helped them has been by Johari et al. 2020, and these are the first people who came up with this multiple randomization design. And the authors of this paper got their the idea from here, and they sort of built on top of this as far as multiple randomization design. Another thing people have been doing has been clustered experiments. And what clustered experiments are, which is in the context of Amazon, let's say, they would group different products, or they would group different people into clusters, and then they would randomization based on that. For example, instead of having a coffee machine and tea maker and things like that separately, they would group them all into one cluster. For example, one cluster for kitchen stuff, one cluster for bedroom items, one cluster for example, gardening stuff. And then they would also cluster different participants, and then they would randomization there. This is one thing that people have been doing in order to avoid, for example, interference. And the rationale for that is that if I'm going on Amazon and I'm looking to buy a coffee machine, if they don't give me faster shipping, I will not go and buy a vacuum cleaner because I'm looking for a coffee machine. I will look for example, another cheaper one, for example. That's why clustering helps sometimes. So they talk about the work that has been done before, and then they start their actual analysis with introducing how they are setting up and with the notation, and then they have some simulations at the end to kind of prove that what they are doing in this multiple experiment design, basically it is an unbiased estimator of the outcome effect, and then they show that by simulations that they perform. So over here, so I will kind of reiterate they assume that they have I buyers, and I can be from 1 to I, it can be any number, and we have J sellers, and J can be a number between 1 to J, and we have assignments matrix here, W, and W can have two values, C for control and T for treatment. In this I times J matrix, we can have different orientation of treatment and controls. And then they talk about a distribution that can be either 0 or 1, but that can be basically between 0 and 1 for the outcome of the experiment, where W is a set of values that the matrix W can take on. So for example, after experiment is performed, each of the items can have an assigned value for their outcome. And then in the paper, they define sum of realized outcomes for each buyer and seller. For buyers, defined with B, they have a potential outcome, which is the sum of individual outcomes for buyers, and for sellers, they have the sum of outcome for sellers. They add that up here, and then instead of measuring the average causal effect after the experiment is done, which has been done so far, which is very simple by sort of subtracting the number of the outcome for the treatment group minus outcome for control group, and let's say this outcome is whether people purchase that item or not, for example, and this is average causal effect. Instead of using this as a measurement, they use a lift. They say in the paper they use lift in order to measure that. And what lift is that it is on the numerator, it is average causal effect, which is the same as what has been calculated so far, but it is sort of in the denominator, it has average outcome without the intervention, and which is only the control groups, meaning we measure the impact of the experiment, treatment minus control, divided by control to get something called lift, or theta in this case, or for example lift. And then they calculate lift for buyers. They also calculate lift for sellers. They also calculate average causal effect for buyers and sellers. And then at the end, they say the reason they wanted to use lift is that the lift for buyers and for sellers and for the overall experiment is the same, whereas average treatment effect of buyers has to be divided by the number of buyers, and average treatment effect for sellers has to be divided by sellers to equal the total average effect. That's why they say it's more handy to use lift, and they talk about this more. It helps them with proving the unbiasedness of the mean estimator and variance estimator. Then they define some basically different frameworks. They define marketplace. For example, a marketplace experimental design is the distribution over W, where the outcome can be between 0 and 1, and the basically probability of all the items in the matrix is equal to 1. And then they say that each of these probabilities should be positive, leading to a value called W bar, and they use that further in proving the theorem. Another definition they talk about is an assignment W induces a consistent experience for buyer I and induces a consistent experience for seller J if W S of J is basically is either 0 and 1, or W of I of buyer is either 0 or 1. And what this definition 2 is in effect is basically what has been done so far, meaning, as I spoke at the beginning of the paper, cellular experiment or bar experiment, meaning let's say this column is product, for example, 8. This product 8 is experiencing being in treatment group across all the population. Or in the case of buyers, this person, let's say person 2 here, experiences all products with a faster shipping option. And that's what this actually here above here means, all 0 or 1 0 or 1 over here. And then they talk about doing some calculations. For example, in this case, in this matrix, the fraction of products and people pairs, or maybe in another word, IJ pairs, the fraction of IJ pairs that are in treatment group versus control is 1 over 4. We have 8 divided by 32, which is for the control groups is 1 over 4. Here it is the same for treatment. We have 8 treatment and we have 32 controls. Here it is also 1 over 4. And then they talk about some additional assumptions that they can put on this, which we're going to get to in a second, that they can prove a theorem. And then they define a general marketplace design, which is a marketplace experiment such that both matrix of buyers and matrix of sellers contain elements different from 0 and 1. So a general marketplace design basically is a design that we don't have something like having all of the values being a treatment group or all the values in the control group. There are some treatment groups involved in for every row. So they define that, and then they come to a completely randomized marketplace design, which is a much more complex version of this basically multiple randomized design, where each of these, if we assume each row is a person and each column is a product, each of these person product pairs has equal chance to be either in the treatment group or control group. So it is very basically it is being randomized across all the I and J pairs. So it is very different from what they talk about initially in the paper. So this is the most complicated case where we have so many different types of control groups, which they do talk about at some point in the paper. And then they, in definition 7, they come to multiple randomized design, which is a general marketplace design in which there is a function. This function is the distribution, which is a functional or a distribution that each of these pairs can be in the control group or the treatment group, for example. And this is what they focus their experiments and their whole theoretical framework on. That, for example, if you have a matrix W for I and J pair in the matrix, it is in the control group if it is for the buyer experiment, the value of W is 0, or for the seller experiment, the value for J is 0. It is in the treatment group if for the buyer experiments it is equal to 1, and for the seller it is basically equal to 1. And what this means is shown over here, and what we talked about. They also have the basically disjunctive form of this. Basically, it is the same as above, but instead of or here, they have and instead of and here, they have or. And what that corresponds to is here, meaning instead of having 3 different control groups and 1 treatment, here we have 3 different treatment groups and 1 control. These 8 treatments are different from these 8 treatments, and also these 8 treatments because of the way they're positioned in the in the matrix, but what they focus on is having 3 different control groups and one treatment. And then they basically go into more detail. There should be a section they go into more detail. They basically formalize simple multiple randomization design, which is a special case of definition 7 above, which is multiple randomization designs over here. So now they talk about this. I keep missing that. Yeah, they talk about this simple multiple randomization design, and what basically simple here means is that we have the assignments in this way. The assignment is basically organized in this way, or in the following way, which is basically shown over here. And then they sort of give these controls some, basically instead of calling them all C's, they try to name them differently. For the red C's over here, they try to call them C, and this C means consistent control. They call this C consistent control, meaning if we basically look at them horizontally or vertically, at no point either the people or the product will face treatment. That's why they are consistency. For the C's over here, the green ones, they call them IB, and this is the updated matrix. IB means inconsistent buyer control, meaning this is, and the reason they say buyer is that it is the control for this person, and let's say each row is a person. For example, Morteza is over here. These 4 controls are controls for Morteza for only these products, but is at the same time this person over here, which is the buyer, is experiencing treatment for other products. That's why these are inconsistent controls. If they were all controls across the board, they would be consistent, but now they call them IB, meaning inconsistent buyer control, and they put them here. And the blue C's over here, they call them inconsistent seller control, meaning for a product, for example, product number 1, and let's say for person number 1, this pair is in the control group, but at some point for another person 3 or 4, this is in treatment group. That's why this product is being randomized into control and treatment for some people and not for another people. That's why they call them inconsistent seller control. And T is for treatment, because we have a uniform treatment. So this is how they formalize their problem. And then they talk about interference and how this interference can be measured, because this was their original motivation in this paper, to try to study something like this. And then they talk about an assumption, a strong no interference, meaning the potential outcomes satisfy the strong no interference assumption if for any pair of I and J and any matrix W and W prime, such that each of the pairs are exactly equal. And the reason they talk about interference, one of the motivations is that if let's say we have this experiment and we perform this experiment, if we want to redo this experiment, or if we want to sort of have this experiment done again on a different set of products or on different people, how this effect can be sort of replicated. And that's why they talk about interference. They want to measure each of the impacts between interactions between control and treatment group. And that's why they say if we have another matrix, W prime, if each of the elements of that matrix is equal to this matrix, then we have a strong no interference, which makes perfect sense because these 2 matrices will be equal. However, there are 2 other assumptions they talk about to kind of sort of relax this no strong interference assumption, and no interference for sellers they talk about, which is the potential outcome satisfied the no interference for sellers assumption if for any pair of I and J and any of these 2 matrices we have only for sellers, only for I primes, or only for sellers, we have the values of the two matrices to be the same. Meaning, if we want to perform this experiment again and want to measure interference for sellers, then we can have the products to be the same, but change the people or participants in the experiment. And there's the opposite of that happening here. Here in the basically, when we want to repeat the experiment, the participants would be the same, but the products they will be shown will be different. In this case, interference on basically buyers is a restriction that is being employed here. There's a fourth case where they call local interference, meaning potential outcomes satisfy the local interference assumption for any pair I and J, and two matrices W and W prime, such that A, the assignments for their pair coincide, meaning for only the I and J of interest, they would be the same, and not every basically pair by pair, but only for that product person sort of outcome would be the same. At the same time, the fraction of treated sellers for the same buyer coincide, and the fraction of treated buyers for the same seller coincide. And this is something they focus on in this paper. Instead of saying we want no strong interference or no interference for sellers or buyers, they say only fraction of treated sellers for the sellers and for the buyers would be the same. That's how they can replicate the experiment. So they talk about a few more things, but in the interest of time, I want to talk about the simulations they performed. They talk about the simulations over here, and the way they conduct the simulations for simple multiple randomization design. They use Gaussian random variables, and they try to mimic the same thing that I just explained above. They have a consistent control group, inconsistent buyer control, consistent seller control, and a treatment group. And each of these F functions are basically Gaussian random variables, and they do that on 5,000 basically different data, and this is the function of F, and they want to check for unbiasedness and for basically formula for variance in these experiments, and these are the results. And as we see, for example, and what they change here, they perform this experiment on I think 3,500 basically data points. And as we see, I think if they did the color coding, color black refers to treatment, red is consistent control, green is inconsistent buyer control, and blue is inconsistent seller control. And as we see, the treatment is different from control, but control itself, we have three different controls, and they each have different means. This is proving their point that there are spillover effects and there are impacts, and we cannot consider controls as just one thing. We can have multiple controls in the same experiment, and they try to do this for different range of outcomes. This is from -5 to 10. This is from -2 to 14. This is from -4 to 12, and they see they have different distributions of controls after performing experiments differently each time. And this is also the experiment they perform to prove the unbiasedness of the average effects. And they have the y-of-c, the red lines here, the dark red ones, are the population basically points or population means. And the orange one, as we see, overlaps on the population one, meaning what they do in the experiment sort of is unbiased in estimating the effect. And then they do that for unbiased for spillover effects. They have the green circles is the average treatment effect for population, and the orange cross is the basically what is measured out of this experimental design, and they see that it is also unbiased. And they do more sort of experiments to show unbiased estimate for variance, as we see over here, and also lower and upper bounds for variance, and basically things like that. So I know over that time, and I apologize if I was not clear at any point. Please let me know if there are any questions or comments.
Thank you, Morteza. That was great.
Sure, thank you. Thank you very much.
Thank you, Morteza.
Sure, thank you. One thing I want to mention to Mohammad Ali and Dr. Jamshidi is that one thing I learned from this paper is very related to our project with Greg, in which case we can have, I mean, we can talk about this more, but we can have, and let's say each column is, basically one of the knowledge questions, and each row is a participant in the study. We can have the same basically experimental design, that having some basically sort of grouping people differently, that some of them be in treatment group and some of them be in consistent control, and add these inconsistent controls here as well to measure the spillover effects, meaning answering correct to one question, does that impact answering to another question? This may be something we can talk about more. Just wanted to mention that.
Yeah, I agree. I have a simple question. Is there technically a formal difference between a spillover and interference, or they use it these two terms as the same concept?
I mean, I think spillovers are basically a spillover is restricted only in when we have a randomized experiment, when we have a treatment group and control group, when some people from the treatment sort of contaminate the control group. That's why they say this has a spillover effect. This is only they use it for basically randomized trials, but interference can be used also in a non-randomized sort of scenario, which is a more broad term. This is what I realized, but I may be wrong.
Okay.
Can you hear me?
Yes.
Sorry, I think you couldn't hear me earlier. I said thanks a lot. This is great presentation, and yeah, I like the idea. Maybe you want to write down a short description paragraph explaining the setup that you're thinking. To me, it seems a good setup. Basically, this split that you mentioned, but we have to review it to make sure that this is correct, and maybe we get some feedback from Greg too.
Sure.
But that's very interesting. If we able to measure like the interference, sorry, this way, that would be awesome.
Sure, definitely. And one point to Muhammad Ali, if you remember difference in difference design, in difference is exactly the same thing we have here, but one of the let's say the column would be time, and then the rows would be each of the participants. And in the difference in difference, what we would do is to subtract treatment from control, and then subtract that from this control minus this control in the case of difference in difference. And this is exactly the same thing, but instead of time, they added another variable like product or anything else. So this was also also interesting, and they do talk about that here as well.
Yeah,
They exactly do the same thing.
yes, their idea is not very complex. It's very straightforward.
Yeah.
And
But it's interesting that, you know, it took so long for people to come up with this in 2021, while difference in difference has been around in like 20 or 30 or 40 years. But what all they did is that in a difference in difference setup, they, instead of time, they said, okay, we're gonna put another variable. So this was very interesting to me.
yeah. Thank you very much.
Sure. If there are no other questions, thank you very much, and happy Iranian New Year's to all the Persians in the call.
Thank you, Morteza.
Thank you.
Thanks. The same.
Thank you. Have a good day.
You too.